You know something? Science is pretty amazing. For thousands of years, people have wondered about the ultimate building blocks of the cosmos. And in the 20th and 21st century, we've made some incredible progress. For instance, if you take a bunch of quarks, Maestro, some quarks please. That's good. And you take some leptons, please. That's good. Oh, wait a minute, a little bit more. Perfect. You take these quarks and leptons and you shake them up, you can make atoms. Atoms, like the ones you see here, make up all of ordinary matter, from me to you to the most distant galaxies. In fact, our best estimates tell us that there are about 10 to the 80. That's a 1 followed by 80 zeros of atoms in the universe. They're all basically the same, and we understand them very well using chemistry and nuclear physics. However, I have some humbling news for you. If you add up all of the matter tied up in stars and planets, it only amounts to 0.5% of the matter and energy in the universe. Even if you include the hydrogen gas between the stars and galaxies that is invisible to ordinary light, you still have only about 5%. 5%. So what is the other 95%, and how is it that we've missed finding it? Scientists think that the universe is composed of 3 different substances. 5% is ordinary matter, 27% is a substance called dark matter, and 68% is called dark energy. In another video, I talked about why we believe in this substance called dark matter. In this video, I want to tell you about dark energy. First, I should tell you that even though dark matter and dark energy have similar names, they are really very different things. Scientists have known for a long time that the universe is expanding and have called that process the Big Bang. From what we understand about gravity, it seems clear that the expansion of the universe should be slowing down. After all, gravity is an attractive force. If I throw this ball up, gravity will pull the ball back downwards. Its motion will slow down. What we didn't know was how gravity would determine the ultimate fate of the universe. Was the universe going to expand forever without ever stopping? Expand and stop at some unfathomable distant time in the future? Or expand for a while, then have the expansion overcome by gravity and have the universe collapse in some sort of big crunch? Nobody knew the answer, and the debate raged. In order to resolve the question, we needed to understand the expansion history of the universe. And to do that, astronomers used a class of supernovae, which is the explosion of a dying star. This kind of supernovae was very well understood. If you saw one, you knew the brightness of the explosion. However, just like a distant candle appears dimmer than a close one, so too it is with exploding stars. By knowing the intrinsic brightness of the explosion and how bright the star appeared in your telescope, you could work out how far away it was. That's the first measurement. The second measurement of distance uses the same idea as a train whistle. That same drop in pitch that you hear as the train passes and begins to move away from you also shows up in the study of distant stars and galaxies. Stars moving towards you appear bluer than the same star when stationary, while stars moving away from you appear redder. The faster the star moves away from you, the redder it appears. Since distant galaxies appear reddish, they are moving away from us. In addition, we can relate their distance and their velocity. If galaxies a certain distance away are moving with a particular velocity, galaxies twice as far away are moving with double the velocity, and so on. In this way, we can measure the color of the distant galaxies and determine their velocity and then work out their distance. It's all a bit tricky, but these two methods of measuring distance are not very controversial, and they should agree. So, in 1998, 2 experiments applied these techniques and looked at the most distant supernova ever. And they found that supernovae were dimmer than predicted by the expansion of the universe. This means that the stars were farther away than expected. But that meant something even more shocking. It meant that the expansion of the universe wasn't slowing down. It was speeding up. That was really a mind-blowing observation. From what we knew about gravity, the expansion of the universe should have been slowing down. We didn't know the details, but the slowing down seemed assured, and yet that's not what the data said. In physics, data is king. If an idea disagrees with an accurate measurement, the idea is wrong. So this meant that in order for the expansion of the universe to be getting faster, there had to be some form of gravity that was repulsive. It turns out that Einstein once postulated a repulsive form of gravity in his equations. This was because he knew that ordinary matter should make the universe contract, and he needed some kind of repulsive gravity to overcome the attraction. However, when the universe was found to be expanding in the 1920s, Einstein took that extra form of gravity out of his equations. He even called it his biggest blunder. Imagine if he hadn't done that. I mean, the dude could have been famous. Now, it seems that we need a repulsive kind of gravity to explain our observations. So what is the source of this new form of gravity? It turns out that if the universe has an energy field of the right kind, it can make the expansion of the universe accelerate. This form of energy is now called dark energy. Now, to be honest, we aren't 100% sure about this dark energy hypothesis, although there are now many measurements that support the idea. Even though dark energy is the most popular explanation for the expansion mystery, other suggestions have been made. While dark energy is a constant energy density, another idea called quintessence is also a contender. Quintessence is an energy field that varies in time, and there are several ideas in contention. We need to understand that the observation of the accelerating expansion of the universe is only about 15 years old. It took a little while to assimilate the discovery and then many years to design and build new facilities to study it better. Over the next couple of years, several new observatories will begin operations to explore this surprising discovery. And I don't know what the final answer will be, but I do know that anytime you don't understand 95% of something, that somebody will figure it out. I won't ask you to be patient because, well, it's hard for me too. But a better understanding of this incredible mystery is just only a matter of time.